For today's notes, you will need in class 70. This is the second and final part of standard 16 where we're learning about volume of three-dimensional solids. So we've got three solids to focus on today: right pyramids, cones, and then also spheres. As a reminder from the last lesson, volume is the space that's inside a geometric solid. And so for a pyramid as well as a cone, we are going to use the volume formula capital B times capital H divided by 3. And then for spheres, our volume formula changes to be 4 pi r cubed, that exponent is a 3, divided by 3. If you'd like more information about where those formulas come from, ask your teacher. But those are the formulas that will give us the space inside each one of these solids. A couple of reminders. Capital H still represents the height of the geometric solid. So for these solids, that's going to be the distance. Instead of being between the bases, it's between the base and the apex. If we were in a prism or a cylinder, it would be between the two bases. But for these solids, between the one base and then the apex. Capital B still represents the area of the base of the geometric solid, and then R shows up in the sphere formula. That's going to be the radius still. All right, so as we work, we are going to make sure that we are carefully identifying the base. So for this first shape, the square pyramid, the base will be a square. Go ahead and highlight that up. Since we're in pyramid mode, volume is found by doing capital B times capital H divided by 3. So if we think about the area of the base square, both our lowercase b and h are going to be equal to 6, which gives us a base area of 36. Capital H is the distance from the apex to the center of the base. So we have a missing capital H for this pyramid. It is connected to this slant height, and it's connected to this distance here, which if we were in polygon mode would be the apothem, but because we're in square mode, that distance is halfway across the base edge. So that will be a 3. So we can use our Pythagorean theorem to help us find that capital H. Across from the right angle would be that slant height of 5, and then we've got 3 squared and capital H squared as our A and our B values. 25 equals 9 plus H squared. If we go ahead and subtract 9, we'll get 16 equal to H squared. And then if we square root, that will give us a height for this pyramid equal to 4. Now that we've got base area and we've got our height for the pyramid, we're ready to substitute everything into the formula. 36 times 4 divided by 3 will give us a volume of 48 cubed centimeters. So just like with our previous volume, we're now filling up these solids with little cubes. So that's why that label has an exponent of a 3. All right, moving to the next one, we can see a clue about the base shape. A regular hexagon is involved this time. We're still dealing with a pyramid, so our volume formula is capital B times capital H divided by 3. When we're working on capital B and we're in regular hexagon mode, that's going to be AP over 2. And it looks like we do have enough information here to find the perimeter. If one side is equal to 8, then that means all 6 of our sides will be equal to 8. So perimeter will be a quick 6 times 8, or 48. We are, however, missing the apothem. So if we draw our little picture off to the side, apothem is that vertical side of that triangle. We know this whole edge is 8, so we can split that up equally to be 4 and 4. And then if we're in a hexagon, that angle at the middle will be 360 divided by 12, or 30 degrees. And that gives us the ability to use our special right triangles to label that with an L, and then this will be our L root 3 side. So 4 root 3 will be that missing apothem that we're looking for. Picking up our base area calculation from there, now that we have the apothem 4√3 and the perimeter 48, we can multiply those together and divide by 2. Keep that nice and exact to be 96√3. So that'll give us capital B, and I'm noticing we actually have capital H available to us this time from the apex to the center of the base, right there, that 15. So we're ready to go. 96√3 multiplied by 15 and then divided by 3. Be careful to keep that answer exact. So we're going to do 96 times 15 and divide by 3, but we're going to leave that √3 out of the calculation so that we can avoid decimal answers that we would need to round. 480√3 cubed centimeters. All right, onward we go to question number 3. This one is a cone, so it'll be a little bit different than a pyramid in terms of the details, but we're still dealing with a volume formula that's capital B times capital H divided by 3. We think about the base of the cone, that's going to be a circle, so we'll find capital B by using pi r squared this time as our formula, which means we need to know the radius, which is missing. So a quick little inspection of this triangle right here tells me that I have enough to use c squared equal to a squared plus b squared, Pythagorean theorem. Across from that 90-degree angle is going to be the c, so that'll be 15. Take care of all of the squaring and then the subtracting. We should end up with, I think, 81. Yep, 81 is equal to r squared, which then square roots nicely to give us 9 as our radius. We'll take that answer for radius and get it plugged in to find our base area. So that will take care of 81 pi. Since we're looking to keep our answer exact, I'm not going to include the pi in the calculation, just leave it sitting right in that answer. All right, all that's left is capital H. That's going to be that height from the apex down to the center of the base that makes a right angle. So 12 is going to be the capital H value. And with that, we're ready to go. Base area of 81 pi times a height for the cone of 12 and then divided by 3. Again, to keep that exact, we'll take care of 81 times 12 and also dividing by 3. So we'll land at 324, which needs to have a pi attached to it to represent the official volume in terms of cubed inches this time. Onward to number 4, we see a cone again. So it's got one circular base for us to track down for our capital B times capital H divided by 3 formula. Still a circle, so still pi r squared. This 8 would be the diameter, so we're going to cut that in half to be the radius. So we'll have a radius of 4 this time, which gives us a base area of 16 pi. Thinking about the other required information, capital H is missing this time, so we're going to go ahead and draw that in right there. And then this can get a little tricky because that capital H is used for more than one thing. But if we have a 40-degree angle right here, that's actually our opposite side, and the 4 would be our adjacent side. So if we transition for just a minute into SOHCAHTOA mode, this is going to be a TOA problem where tangent of 40 will be equal to that opposite side, which is our height, capital H, divided by our adjacent side, which is 4. A quick multiplication on both sides by 4 will get that capital H height to be by itself. So 4 tangent 40 goes into the calculator. I'm not actually going to round that. I'm going to write a few extra decimal places on my page, but I'm keeping that whole decimal in my calculator so that I can use it to finish up volume, keeping it nice and exact. So even though my page looks like it's been rounded, I'm going to take 16 pi and I'm going to multiply by that whole answer in my calculator and then divide it by 3. So there's my capital H height. We're going to multiply that by 16 pi to finish out the top part of that fraction, and then divide that by 3. This is the moment in time when we officially round. So 56.24 cubed centimeters for the rounded volume of that cone. All right, go ahead and flip the page and meet me back here for the rest of our examples. Onward to number 5, we've got another cone that we're dealing with. So we're going to stick with our capital B, capital H over 3 formula. Base area is still the circular area, so we still need the radius, which happens to be missing this time. But we have a clue this time about a 60-degree angle. So this is actually going to be our shortest leg. So that's not L as in slant height L, that's L as in our 30, 60, 90 shortest leg. And then across from the 60 is the L root 3 side. So this doesn't match up super nice. We can divide by root 3, but then we get stuck. And so to simplify that, hopefully you remember that we rationalize the denominator, or some of you have teachers that tell you to go back and instead of dividing, multiply. So you can do that instead if you're more familiar with that. But this will leave us with 6 root 3 in the numerator and regular 3 in the denominator, which becomes a 2 root 3. So our radius is going to be equal to 2 root 3 for this cone. Now remember, squaring those radical expressions can be a little bit tricky. So we're going to square the 2 and the root 3. That should give us 12. So our base area for this cone will be 12 pi. We already know the capital H height going through the center of that cone. So now that we've got our base area tracked down, we're going to multiply that by 6 and divide by 3 to finish out the volume. 12 times 6 divided by 3 is going to land us at 24, with a pi still attached to give us an exact answer. And then the units this time will be cubed meters. All right, looks like that was the last cone problem. So now we're shifting over into sphere mode. The volume formula for a sphere relies on 4 pi r cubed over 3. So all we need is the radius, which we have. But we do need to use our calculators well, because we need to do 3 cubed, and we are used to squaring. So on your calculator, instead of clicking the normal exponent button, we're going to end up using this little caret, this little like arrow up. That allows us to change the exponent into something else. So if we're keeping our answer exact, we're for sure not going to include pi, but we're going to do 4 times 3 raised to the 3rd power. Now this calculator makes it look like 3 cubed, but other calculators, that little caret will just be sitting there, and it will end up looking like 3 caret 3. It will take care of the exponent part for you though. So that will be 108 pi. What's really happening here is 3 times 3 times 3. That's what cubing is. So you could also just type it in like that and then multiply it by 4. And then we need to test to see if that can be divided by 3. This one can and stay exact. So that means our exact volume for this sphere would be 36 pi. And then our cubed centimeters for a label. If that division had caused a repeating decimal, then we just would have left our volume in fraction form. And that would be considered an exact answer as well. All right, number 7, same situation. We're in sphere mode, so 4 pi r cubed over 3. This time, though, the 10 is the whole diameter, So we need to start by dividing that into 2 so that we have our radius. So 4 pi 5 cubed this time over 3. Taking care of the numerator, 4 times 5 cubed will be 500. If we do a quick check, we cannot so easily divide 500 by 3. So the best way to leave your answer this time is 500 pi in the numerator divided by 3. Nice and exact. That's a simplified fraction. It doesn't require us to do any rounding. All right. Our last 3 examples are examples of composite volume, which means we're going to need to use some of our formulas from before, and we might need to be able to make some adjustments and decide whether we're going to be adding volume together or subtracting volume. So for number 8, the bottom part of this would be a prism, and the top part of this would be a pyramid. And when we stack those up, none of the volume goes missing. It's just that flat base that's now stuck on the inside. So all we need to do for that volume composite problem is add up those 2 volumes. So if we come over to the side and we think about prism volume from the other day, that's just regular capital B, capital H. If we think about pyramid volume from today, that's going to be really similar, but divided by 3. All right, prism base looks like it's 8 by 8. So that base area, 8 times 8, would be 64. And then the height of the prism part of this is going to be 5, the distance between the bottom and the top. So 64 times 5 will give me the prism volume to be 320. So that's one part taken care of. When we get to the pyramid, we still need base area, which it looks like will match perfectly with the prism. So I can reuse that 8 times 8 or 64 number. But the height of the pyramid is here through the middle, from the apex to the center of the base. So that's not equal to 5 anymore. That's actually equal to 6. So my calculation this time will be 64 times 6. And then remember to divide that by 3, since we're dealing with a pyramid. 128 for the pyramid part. So total volume, that 128 and that 320 should be added together. So total volume for the whole composite figure will be 448 cubed meters. Just adding those 2 together. Moving to number 9, doesn't look like prisms and pyramids anymore. I see a cylinder for the bottom section, and then this dome is going to be half of a sphere, otherwise known as a hemisphere. The cylinder part of this from yesterday is going to be found by doing capital B times capital H. But that half sphere is going to require me to take my formula for the regular sphere, remember that's 4 pi r cubed, and divide it in half. So instead of 4 pi r cubed, half of that would be 2 pi r cubed divided by 3. All right, looks like we have our radius. So when we're thinking about the base of the cylinder, that circle on the bottom or that circle on the top that matches it, that would be found by doing a pi r squared calculation, where 6 is the radius. So we've got 36 pi as that base area. And then the height between those circular bases looks like it's going to be 4. So 36 times 4. I'm going to leave the pi out for right now so that I can keep it nice and exact. That's my goal at the end anyway. So the cylinder volume will be 144 pi. Moving to the half sphere or the hemisphere, that radius is consistent. So I can keep using 6 as my r, but I need to make sure I'm careful here to do 2 times 6 cubed, not squared, but cubed. So that'll be 432. And then let's see if we can divide that by 3. Oh, we sure can, and we end up with 144 again. That's a coincidence. So the half sphere is also 144 pi. Those are definitely like terms, so we can go ahead and add those together to find our total volume of 288 pi cubic centimeters. All right, 9 examples down and 1 to go. Thanks for hanging with me here. And this one is a little bit different. This one has an empty section, so volume has been removed or taken away. So that whole outer shape is a prism, and then we're going to take that cone volume out, empty it out, which means we need to subtract it. All right, for the prism, capital B times capital H again. Looks like the base is still a square, this time 6 by 6, so base area of 36. And then the height between that base and the top base for our capital H would be 6. So prism volume 216. That's too much though. We need to get that cone volume removed out. So for the cone, we're going to have capital B, capital H over 3 from earlier today. We need to be really careful we use the base of the cone this time though, not the base of the prism. So when we're thinking about the base of the cone, I'm going to show my work for that. That's a circle, pi r squared, where the radius is given to us as being 2. So base area for the cone is 4 pi. And then because that cone goes all the way through that prism, we're using the same capital H of 6. 4 times 6 divided by 3 is going to give us a volume of 8 pi for the cone that needs to be subtracted away. Since those are not like terms, I don't want to do 216 minus 8. I want to actually do the whole calculation at once. So 216 minus 8 pi, that will create decimals, but that's okay because our instructions tell us that we are giving a rounded answer for this problem. 190.87 if we're rounding that carefully to 2 decimal places. All right, so 2 composite figures where we're adding volume and then 1 where volume's actually been taken away. That's it for your volume notes. Thanks for watching. We will see you back in class.